Okay, so the slope represents the average rate of change of f with respect to x for some interval between x and x plus delta x. Now, does this average rate apply to every point in this interval? This closed interval from x to x plus delta x, and I assume you understand interval notation. Well, maybe it does, maybe it doesn't. We don't have any further information. So for any point in this interval from here to here, we assume, we can make the assumption that the average rate is the same as it is for the whole interval, but we also know that that might not be the case. It might be the best assumption we could make because we don't know anything else about whatever this function is representing. Okay, so let's actually then consider, fishing for a piece of chalk here, let's consider what happens if we have additional information. Okay, so let's say that we've now got a different value of delta x, giving us a point somewhere between here, and we happen to know the value of the function at this point. So now we've got a point which is an x plus delta x, but now we've got a different delta x. Now I could use notation to indicate that, but I'm going to write this one in purple. Okay, so now we've got a new delta x. So this is not the same as this delta x, even though the symbol looks the same, and I'm taking a few liberties. This is x plus a new delta x, and let's just call this delta x, just to have a notational difference, delta x hat. So this point is x plus delta x hat. I've put it in purple, but I've also put a hat on it. And we have a point on the graph. Okay? Now this point might lie on the straight line that we use to connect these 2 points, the slope line from this point to this point. But it might lie above it, it might lie below it. So what does that do to our thinking about the average rate of change? Okay, well, if it's on the line, then the slope is going to be the same and the average rate of change is going to be the same. But if the value of the function at this point, in other words, if f of x plus delta x hat is greater or less than the value it would have on this line, then we're going to have a different slope. So I'm going to say, okay, let's say now that we have a point here, and of course then if this is a point on our graph, then right here we have f of x plus delta x hat. So I'm going to write that as f of x plus, and I'll write my delta x hat, and as usual I didn't leave myself enough room here. Might have been better if I'd have put the point lower here so I'd have more room to label it, but that's f of x plus delta x hat. Now we have a different slope. Okay, so, and the slope here, of course, we have f of x here on the line, so that the rise between 2 points of this segment would be f of x plus delta x hat minus f of x, and the run would be just from here to here, which is just going to be delta x hat. So now the purple slope is f of x plus delta x hat minus f of x over delta x hat. and that slope is greater than the slope of this segment. And this slope represents the average rate of change of the function on this smaller interval. Okay, now which average rate of change do you think would be closer to the actual rate of change of the function at the point x? How quickly this function is changing with respect to x at this point? Well, this being a smaller interval and these points all being closer to this one, we'd probably say that this one is going to be closer to the average rate, to the rate of change very near x. Okay? Now suppose we have another new point, and I think I'm out of, no, I got green here. Okay, I think I'm out of colors, but I'm not quite. Okay, so let's say we have another point, and this point is maybe right here, not quite directly above, but the slope at this point is a little greater. Okay, then we would say, well, you know, the trend of the slopes, if I take them over smaller and smaller intervals, is to get bigger and bigger. Okay? So the slope appears to increase if I take an interval closer and closer to x. So now I ask myself, as delta x gets smaller and smaller, what happens to the average rate of change of f with respect to x? Okay? Well, the answer is that it approaches a limit. If there is a limit. Now, there doesn't necessarily have to be a limit. For the functions we're used to talking about and thinking about, you know, they're nicely behaved functions, and there will be a limit. But there are functions that we can construct that would not have limits. Okay? So, I can say this, and I'll write this in red for emphasis. If the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x exists, then a couple of things. Then that limit doesn't apply to any point except x. Okay, because we're letting delta x approach 0. Okay, any point, no matter how close to x, that isn't equal to x, the x plus delta x will eventually get closer to x than that point. Maybe think about that. Okay, if this limit exists, it applies only at the point x. That doesn't mean that there aren't other points that might have the same limit, but they don't have the same limit for the same reasons they do at x. Okay? Applying only at the point x, we have to have a name for that limit, and that name can only apply to the function f and the point x. Okay, so we call this limit f prime of x. And name it the derivative of x at x. And we'll observe that that limit represents the rate at which the function is changing right at x. Not at x plus 1/billionth, not at x minus 1/trillionth, but at x. So we call this the instantaneous rate of change. And I ran out of room to write that. And I'll abbreviate rate of change by ROC of f with respect to x at x. Okay? And we kind of need all those words to be very specific about what it is that we're seeing and what it is that we're talking about here. So this is the definition of a derivative. And the derivative represents, at the instant, how quickly f is changing with respect to x, or the rate of change of x with respect to x at the value x.